Number 5 here. So they give us a polar curve. They ask us to graph it. And depending on the year that you're doing this with me, we may not have talked about this. You did it in pre-calc, hopefully, but I'm just going to roll with that we're using our calculator for this. So notice r equals 2 sine theta. I am in polar mode. I guess it doesn't say it up here, but I'm graphing in polar mode. And this says sine 2 theta. That was the best I could get for the screenshot. And then what it did was it graphed this, and it went around like this, wink, and then stopped there. The reason I have the window here is because I want you to see that it goes from 0 to 2 pi. And what that did was it drew the whole thing like this. Hopefully we talked about how to do that kind of analysis. We want to find an integral that represents the area inside the total curve. So what we can do is, since it took from 0, there's a variety of ways to do this, but since it took from 0 to 2 pi to do the whole thing, then those are going to become our bounds. You should know that area in polar is 1/2 integral theta 1 to theta 2 of r squared d theta. So my theta 1 and my theta 2 are going to be the length that it took, or the theta values that it took to draw this whole curve, which it started at 0. That's what that would say if it had screenshotted it well. And it ends at 2 pi. So my area is going to be 1/2 integral 0 to 2 pi of boink squared d theta. And all you have to do is put the function in for r. So we're just going to write sine of 2 theta squared. Oh, sorry, it's already there. Erase. There. So that's it for that one. You just 1/2 integral from starting amount to ending amount of the r function squared d theta. There's a variety of other ones we could do, but I'm just going to roll with this one like this. Actually, I'll comment on it real quickly. All of these leaves here, or petals, are all exactly the same length. So if you wanted to integrate this one with the 1/2 and then multiply it by 4, it would give you the same answer. Sometimes they'll do that on the AP. All right, so I'm going to answer C here. If we didn't cover arc length or perimeter of one of these things, you can ignore this part of the video and then go check out some of the other ones. But I'm going to go ahead and do this in case I did cover it. So in polar, arc length, actually we'll just go and write L for length. Length is equal to the integral from theta 1 to theta 2 of the square root of, there's a couple ways to write it. I'm going to write r prime of theta squared plus r of theta, squared d theta. So, a couple comments. We know that this is r. This is r. So that is going to slide in here. I need to find r prime. So let's do that. I'm going to do it down here. R prime of theta is the derivative sine of 2 theta. I get a little chain, 2, and then I get a cosine of 2 theta. Sorry, software's getting a little weird there. All right, so what were we doing? This is going to become this, and this is going to get replaced with this. So I'm going to actually, we'll do it all out. And here we go. So we get that this is equal to integral. Let me talk about the bounds real quick before I plug those guys in. So 0 to 2 pi was the full thing. They're asking for one leaf of the curve. So I got to divide 2 pi by 4 to get just one piece there. So 2 pi divided by 4 is pi over 2. So I'm going to go from 0 to pi over 2. of the square root of boink. What do I get? 2 cosine of 2 theta squared plus sine of 2 theta squared d theta. And then all I'm going to say here is that you should probably simplify this out a little bit. That gives us integral 0 to pi over 2 of the square root of, this is the same as 4 cosine squared of 2 theta plus sine squared of 2 theta. I'd probably take either one, but if this was a multiple choice question, the answer would probably be written in a form more like this. So, there you go. Hopefully you're good. And I'll make a video for 6.